Welcome to the tutorial on OmicSelector, an environment Docker-based application in R package for biomarker signature selection from high-throughput omic experiments. My name is Konrad Stawisky. I'm the radiation oncologist and PhD candidate at the Department of Biostatistics and Translational Medicine at the Medical University of Łódź. I'm also one of the authors of the software, so I will be showing you what the software is capable of and how you can use it to select the best biomarker set. The main purpose of OmicSelector is to provide you with a set of candidate features for further validation in biomarker study. The package performs feature selection first, and then in the next step, which we call benchmarking, those sets are tested using various data mining methods. And based on average performance of sets in cross-validation or in holdout validation, so meaning testing on test set and or validation set, we can suggest which of the signatures is having the greatest potential in further validation. So after providing the data into the pipeline, we can do some pre-processing, including missing data imputation and batch removal using Combat. The pipeline can be also used for easy exploratory analysis. We can perform principal component analysis, differential expression analysis based on t-test. We can generate heat maps and volcano plots. And the main purpose of the application is to generate the overfitting resilient set. So we achieve this goal by splitting the data set randomly, or you can provide a split into training set, testing set, and validation sets. Based on the training set, we perform feature selection with 60 methods. We perform filtering of feature sets based on previous number of predictors. And those feature sets are tested in the process called benchmarking. We apply multiple data mining methods to develop the best classifiers. Those are optimized based on their performance on the testing set, and later are being validated in the independent validation on validation set. After we combine the metrics from the various data mining models, we can suggest which of the set is performing in the best manner. In the last step, you can use our deep learning module to develop a best performing deep neural network, meaning feed-forward neural network up to 3 hidden layers, and develop a final classifier, a final classification diagnostic model, which can be hopefully published. The final analysis report looks like this. So we start with the analysis ID, and then this is the initial check of the file which was provided. There are several pre-processing and post-processing extensions we will cover later. Exploratory analysis. In this section we can see the generated heat maps. Those heat maps can be customized using the tool in the pre-processing section, but here this is just a general overview of what we have in the data. So those are the heat maps of all variables, significant variables, including the class variable, including the split into a training, testing, and validation sets. We can look at it here, and also the batch effect, whether it is appearing in the data set or not. Those heat maps are based on the expression values provided, or can be also standardized using z-score before plotting in the image.
After we move forward, we can also see that there is also a plot for principal component analysis in 2D. The pipeline can also generate a three-dimensional plot, but we can show this later in the differential expression analysis tool, and also the volcano plot, which can be also modified in this module. Training, testing, and validation sets can be viewed here or downloaded. Using the download button is quite helpful because you can later upload those files, those specific files, into the pre and post-processing tools. So you can also click the view to view it in the browser, and also to filter it and have a general preview of the data. You can also redo the initial check and default exploratory analysis. This is great if you want to customize those plots. You do not have to write the code, you just have to click the run, and it will open a Jupyter-based notebook, which can be used to generate and modify those plots. Of course, the Jupyter notebook has its own environment that works as it should, so pressing Ctrl-Enter will execute the code, so you can see that it is working or not. You can also see how the file is being checked and how the differential expression is performed in the pipeline. If you want to customize this analysis, you can also click Create Your Own Analysis, and it will give you a rough skeleton, which is loading the data. And as you will load the data, you can insert the cells and play with them as you like in the code if you have the knowledge. This is obviously an extension which can be used, but it is not necessary to perform whole analysis. So after we will perform a feature selection in feature selection module, the pipeline will list the name of the feature selection method used, the features which were selected, and the number of the features which the pipeline thinks is the best, which those features are selected by this particular method. We can easily download the data set with those features only using this button and look whether this will provide us a file with limited number of features. Okay. As we move forward, we can see all formulas selected by the methods, the final set of formulas selected by the methods. We can also view the log or add and rerun some methods if we want. After benchmarking, we move to the section which should help us to choose the correct signature for our further validation and further studies. So first of all, we check overall methods performance. In those graphs, we can see plotted the box plots showing us the accuracy on training, testing, and validation sets using different methods. This can tell us whether one of those methods are particularly prone to overfitting or resilient to overfitting. For example, this random forest here can really see that the accuracy is really great on training set, but it is dropping drastically on the training and validation set. So this is probably not so very good methods for this. In the next section, we see the top 3 sets which achieve the best accuracy in training, testing, and validation. We determine it by using the meta-index value, which is the mean of all 3 accuracy metrics. So accuracy metric on training, on testing, and validation set. And here in this example we can see that the greatest meta-index was achieved by this method, and it is showing us that we should use just 2 microRNAs to distinguish cancer and control cases. We can also see that in the plots that are provided in the next section. So here we can see that for the modeling method called GLM, so this is geologistic regression, it is all well documented on the website. We can see that this model achieved accuracy of 79.1%, sensitivity of 81%, and specificity of 75.4% on training set. And you can also see what was the area under the curve with its 95% confidence interval. You can also see how this model performed on testing and validation set. So basically every method, every feature set is having its own plot for own method, and those results are provided in this very long section. And of course those plots can be used to summarize how the model is generally performing. We can also assess the overlap of those signatures, and we see that those 3 best performing signatures had one feature in common, and this one common feature is of course the feature presented here below. You can read which features are where based on this section here. We also test whether we could achieve different results if we calculate the meta-index based just on 2 metrics, so the best accuracy in testing and validation sets. And here we can see that the same features were selected, and this is constructed in the same manner. So we also see the different models constructed on different features using different methods based on which we can pick the best model in this benchmarking section, and based on which we can make an informative decision about the overfitting in our set. And of course the overlap is also presented here. We can see which features are overlapping with which sets. There is also a third option in which we just show the same thing, the same metrics, but we are interested in the mean of sensitivity and specificity just in validation set. This is of course optional, but can also provide additional insights into whether your features are working or not. And in the general analysis, first we perform the overfitting analysis. So we plot top 6 sets, and we are checking how the accuracy is dropping in which method and in which feature set. We can assess it graphically. We can also see the relationship between accuracy on testing and validation sets and the best feature set. The best feature set is performing on this first meta-index, which was calculated, so the mean accuracy in training, testing, and validation. So this was the signature. We can also see the differential expression of those particular features, whether they are significant or not in the differential expression. There is also a heat map generated for those features. This of course can be modified in the particular section in the pre and post processing tools. And we also see a table with the best classifiers, where we can see the modeling method, the selection method, and the metrics like area under the ROC curve, accuracy in training, accuracy in testing, and accuracy in validation. The calculated meta-index 1, which is the accuracy in training, testing, and validation, and meta-index 2, which is just testing and validation only. And the best model is shown here. So the best classifier should be this model. Sorry, this model. Yeah, with the greatest meta-index, and it is having this confusion matrix in the training set. Great ROC curve, quite good accuracy in the testing set, but we can see a significant drop in sensitivity, and quite and very well performing model in the independent validation set. Based on meta-index 2, different model is selected, and this model is not so perfect in the training, and testing and validation set may the metrics may look more promising to you, as less overfitting obviously is present here. The benchmark results can be viewed in the browser, so we can see the method, the features selected, whether this has used balanced dataset or not, and the model name because you can extract the model and reuse it in different scenarios, area under the curve with its 95% confidence interval, lower and upper values, accuracy, sensitivity, specificity on training set, on testing set, and in validation set. And this prefix here is defining us which method was used in the modeling. So for GLM it is logistic regression, MLP is multilayer perceptron, SVM is subprojector machine, and so on and so on. RF is random forest. Those are explained in the documentation, and you can pick them in the benchmarking. And there is a simplified version showing you the different models with different IDs, the modeling method and the selection method, and its performance metrics. If you would like to reuse this model, you can browse those models, download the R file, and use caret package to implement it in your own application. We can also customize all of this and try to tweak with this report. You can see the code, how it was prepared, and you can customize every step of the analysis if you would like to play with the code. We can also refresh the best signature analysis, so this will generate this document once again and rerun benchmarking. We always consider deep neural networks to be the best tool to develop simple or complex classification methods. This is why we have implemented the deep learning grid search pipeline in our software. So first of all, you perform a training of deep neural networks with grid search of hyperparameters. You can use autoencoders or not, but generally the neural networks generated are the feed-forward neural networks with up to 3 hidden layers and with different hyperparameters as shown later and in the documentation. So neural networks can be trained in different batches, and after we will finish with training what we want, we can merge all deep learning runs and download the results. it will be a huge file, so I would rather say that downloading a file is safer than viewing it online because it can take a lot of the time. So after we merge it and sort it by meta-index, by using this mean of training, testing, and validation accuracy, we can see the top 1,000 performing neural networks. We can sort them based on the meta-index and select the best performing model. So as we look at the file, we can see the hyperparameters like the neurons in the layer, the activation function, the dropout rate, whether the regularization was used, the optimizer, if the network is having autoencoder before moving to the modeling, the formula, so which features were used, whether this network is scaled, so using standardization before the actual model induction, the model ID, which can be used as a reference, the training area under the curve with its 95% confidence interval, the value of cutoff of the probability which we use in the prediction. This is based on the Uden index. I will show you that in a second. The training accuracy, sensitivity, and specificity, also the positive predictive value, negative predictive value, and F measure. Those metrics are also calculated for the testing set and the validation sets. The name, which is similar to the ID but has also a prefix, so this is probably more worthy. Whether this network was worth saving, we do not save the model files, which are performing very poorly. So this is why we use it. This is not you cannot set it in the general user interface, but if you are using R, you can modify this threshold, the training time, and the value of the meta indexes. So after you will pick the correct network, you can see it how it is working. Here you can just pick the network which you like and open our tool for the neural network model viewing, and you can see that first of all the hyperparameters are loaded, so you can see all the metrics once again. The ROC curve with selected cutoff based on the Uden index, we selected in the training set phase. You can read about it in the log file here. So here the optimal cutoff was chosen with the Uden index like this, and the accuracy, sensitivity, and specificity. So this is generally a training log. You can see the structure of the network, the list of the metrics in the training process, the selection of a cutoff, and the training performance, testing performance, and the validation performance of a neural network. And in the last step, you can see training and testing induction curves, how the loss and the accuracy was changing during the training process. You can also download this model file. This is a zip file which is containing a lot of the information and can be also used in this application to load this model. If you want to use it in a prediction, you can use tab predict single case and modify the case inputs and see how the prediction is changing after changing the values here. You can see that those values are changing. Let's set something extreme so we can see a difference. Yeah, 0.44. But please note that the cutoff is still being used here. So as you will select different options, you will see different results in this prediction section. So for this particular metrics, for this particular results, you can see that the prediction would be control with this prediction probability, and the details are here. So the network configuration, once again, new dataset which was provided, new dataset after scaling if the network is scaled, network features, the cutoff value used in this prediction. Those are the values used in the Z scoring. So in the standardization, if the network is scaled, because we do not know what the class is, we cannot provide a confusion matrix, ROC or ROC under the curve, but you can do it if you will upload the CSV file with prediction. So welcome to OmicSelector main application screen. Here we can see welcome message with the current version of software, the analysis section, the pre-processing and post-processing extensions, and additional tools. There are two types of analysis which can be performed in OmicSelector. The first one is OmicSelector analysis. It involves feature selection, benchmarking, deep learning, and eventually selection of the best model, best signature, and everything we have shown so far. If you are not interested in this step, or you want to customize everything, you can start with new custom analysis. It will just give you the access to the environment, to the package, and to the additional tools running within the analysis. And let's start the new OmicSelector analysis so we can explain how the file should be prepared. So let's open the exemplary file on GitHub and see whether this file matches all the assumptions we should have. So first of all variables which column name starts with HSA will be considered features of interest. We think that the most common scenario is the selection of human biomarkers, and those usually start with HSA prefix. So this is why we have constructed the pipeline like this. So every variable which has HSA at the beginning will be considered a feature of interest. All values which name does not contain will be considered as metadata. So sample class will be a metadata in this example. The dataset has to have a variable called class with no missing data, and with values explicitly encoded as case and control. So you can use a different name, like in this example cancer and control, but those will be encoded by the software as case and control. You can define it here, value of class of interest. So as I have cancer in my data, those will be recoded to cases. Okay, if your problem does not involve cancer detection, please temporarily change your encoding and interpret the results accordingly. So the pipeline will perform data splitting into ratios 60%, 20, and 20%. If you wish to enforce your way of splitting, the file should contain the variable mix, and with values train, test, and valid as shown here. This will cause the pipeline to omit the random splitting and use just your own splitting. The splitting is necessary if you want to have all the features of the application. If your set is too small and you think that splitting may harm your results, you can set here the value to no, to oversampling training set to create a testing and validation sets. Of course, this will have implications in inference after the analysis, but you can try to use it in this way. You can customize the random analysis ID. This will help you to resume the analysis if you will exit the software. it is randomly set here, but you can customize it to anything you really want. And the type of expression data is quite important because it will be associated with different calculation of fold changes in differential expression analysis. So it can really change your results. So if you have log10 transform data, please use this option, like in log CPM, log TPM from new next generation sequencing experiments. If you have crude values like delta CT, some kind of related expression which is linear, you please use crude values here. So in my case, it will be log10 transform values, and let's select our file. So this is the exemplary file used in the analysis. Let's click upload. This will take a while to check if the file is fulfilling all the assumptions and to generate the basic exploratory analysis. But as we move forward, we can see that initial check status, the file contains class variable, the class variable was converted successfully, so the original values are saved in class original values. The data contains controls and cases, also contains 192 features for selection. In our case, those are microRNAs. All features are numeric, there are no missing data, and so on. So the initial check status is okay. If you experience an error, you have to unfortunately fix the error as per instructions provided here and re-establish the analysis once again. You can view this data using the viewer. So everything looks okay and it was imported successfully. You can import CSV file or the spreadsheet in Excel. Okay, you can play with the pre and post-processing extensions, but let's take a look at the exploratory analysis. So everything is set up now. We can view or download the sets. We can view the differential expression analysis. So in the next step, we would like to perform our feature selection. We can omit deep learning. For now, we will focus on the feature selection. You can see that in the deep learning, we just would have to create neural networks with all features. So we have to start the analysis. So in feature selection, there are multiple of feature selection methods which can be enabled or disabled. And those methods are briefly described here and in the documentation of the package. Some methods require you to set the preferred number of features. So if your problem involves, for example, next generation sequencing like small RNA sequencing and further development of a validated test using qPCR technology, you probably want to limit it to maximum of 10 features. So this is where you can do it. Some methods are really computationally extensive. They may require a significant amount of time. So because we do not want to wait eternity to do it, we can set up a timeout for selected methods in seconds. So 360, so 1 hour is set up by default. And in some methods, like genetic algorithm, you can also tweak the maximum number of iterations of the algorithm. It will also significantly impact the amount of time which the application requires to get the results for you. So let's start the feature selection after we have set everything what we want. So the analysis is starting, and in the panel you can see that the task is in progress. You can cancel it anytime, and there are last 10,000 lines of the log here. So the task, as you can see, is running. You can download whole log file. It is refreshing automatically. As you are waiting, you can also try to play with additional tools to do something more in the meantime. So as the feature selection is finished, we can see the methods and features selected by those methods and also the count of those features. Here we can see all features. So for example, those methods have all shown the same set. Those will be aggregated before benchmarking, so don't worry about it. This is just to show you which method was selected where. You can view those methods in the table. You can download this table, you can analyze it. You can also try to do some more methods, pressing this win button and adding more methods or redoing the methods which rely on the random processes. You can also view the results here. So in the next step, we want to benchmark those signatures. So we will go to the benchmarking section which appeared now, and we can select which data mining methods we would like to check. So first of all, we can select all of them. Please note that extreme gradient boosting may be very long, so this is why this is disabled by default, but if you have this time and resources, why not? There are several methods here, like logistic regression, support vector machines, random forest, decision trees, and so on. And in the options, you can also set a number of random hyperparameter sets, because the hyperparameter search here is using a random search. So we should select some good value, like 200 or like 2000, to be sure whether there is no bias associated with selection of hyperparameters. And the type of validation, we can use holdout validation on a test set, or we can use a 10-fold cross-validation repeated 5 times if we do not want to introduce bias associated with testing on the test set. But generally we recommend it that you use holdout validation on a test set. This is how we can try to make those models with the best hyperparameter sets optimized for a test set, but not validation set. So the concept of independent validation is still intact. Okay, so let's start at benchmarking. So the process is started. Please note that the algorithm is also assessing the server load. If the server load is greater than 80%, it will wait in the queue. This is just a thing that can keep your application running smoothly without overloading. So the benchmarking is working. We can see the results in a second. Okay, so OmicSelector task is finished. We can see that it is finished. We can view the log, and we see that the task is finished, and we can go forward and see the results of our benchmarking. Let's scroll it down. Okay, so this is the best signature analysis we have already seen, and all the results that we have already discussed, along with the volcano plot, the best signature, and the metrics. So the last step we would like to do is to create a better model, because the best model so far has the best accuracy on training set, quite moderate accuracy on testing set and invalidation set. The sensitivity 80%, 56, and invalidation 73 and 75. Maybe we will achieve something better using deep learning with Keras. So let's see which selection method was the best. So this with Boruta, this is the best classifier so far, and the method used was random forest. The best set seems to be the set selected with selected in differential expression, so maybe we can use this set. So significant top non-Ferroni smoted, so we use the balanced data set. So let's go to the deep learning section and let's select this set. This is the set. Let's do not do a full scan or extended scan. In real-time projects you should do it. So the extended scan is developing neural networks, have to 3 hidden layers with and without autoencoders. So it will develop almost 300,000 hyperparameter combinations, so 300,000 networks. In the full scan, there are no autoencoders, so neural networks will be developed in the straightforward manner, feed-forward with input values in the input layer, and there will be a grid search of hyperparameters with up to 3 hidden layers, and the quick scan with just with 1 hidden layers and without autoencoders. We know that balanced dataset was better, so maybe we should use it now. And yeah, let's. This number of parallel training processes is highly dependent on the equipment you have. If you have a CPU or GPU, it should be usually the number of the threads you have. In case of GPU, this is really experimental. You should try to tweak this parameter on your own. So let's start deep learning. Deep neural networks are being trained now. We can see the finishing of networks, but it will take a significant amount of time. So let's talk about the additional tools. So first of all, those tools are not available in public implementation because it would create a serious security issues. However, they are the most powerful IDEs, so they can really be helpful in development of new analysis, in customizing your analysis. So first of all, Jupyter is loading automatically and to the directory where is your analysis, so you can see all the files created by the pipeline so far, along with the R codes used to execute the pipelines. You can also see a differential expression results, starting data file, test set, training set, and validation set, model results, and so on and so on. Of course, everything is editable, so if you will click on it, you will open it in the Jupyter notebook, so you will be able to edit those files. Yeah, let's wait a second for it to load. The system is really overloaded now because of the training. You could also run terminals and the extensions of the Jupyter, so you can customize everything as you like normally. So yeah, it is loaded now, so you can see all the code chunks and you can customize everything on your own. The second thing we can have here in the analysis is the RStudio. The RStudio, as you will click the RStudio button, it will first of all create a user, so you can use everything what is available here. Login credentials are provided here, so basically your analysis ID should be your username. Password is by default OmicSelector here, and this will run the RStudio. Let me show that to you. And you can successfully log in to the RStudio for the further analysis. Okay, Radiant. Radiant is provided for you, so you can make an exploratory analysis more useful without coding. Radiant is a tool which is available online and is open source. The application hosts its own version of it. So first of all, you need to be a little patient because all of those files are converted to the Radiant objects, so you can easily load them. Let me show that for you. So as the Radiant will start, you can load additional data from the analysis using this load button. It will show you the files which are converted from CSV files in your analysis directory, and it gives you a lot of the details. You can view, plot the data, and try to do simple modeling. It will for sure help you in deciding your next steps in the analysis. And the last tool, the most powerful tool, and the tool which can allow you to do everything, is the Visual Studio Code. And as you can see, the Code Studio is loaded, and you can experiment with it, also installing the extensions and make it a powerful space for your project. So this is why we are giving you the option. We are giving you the option to start your own custom analysis. And if you will start the custom analysis, you can do everything with those tools. Just pick then your ID, and in this custom analysis panel you can see the additional tools like Jupyter based notebooks, RStudio, Radiant, and VSCode, and you can use them along with the additional pre and post-processing tools. So there are also Shiny applications which can give you additional insights into your project and can help you in performing the analysis. First of all, differential expression. Let's load it. In the differential expression using corrected t-tests, you of course have to upload the data which are consistent with the OmicSelector format. So let's use the file we have provided previously. Okay, and as if it is loaded correctly, you can see the principal component analysis. Principal component analysis in this 3D interactive graph, volcano plot, and the differential analysis results. so the mean, expression, median, and standard deviation for cases and for controls. You can also download this file using this button. So it shall load smoothly into the Excel or any other software. So we have here log to fault change, p-value, and p-value corrected with unfairly home, and BH, so or FDR correction. You can also change which microRNAs should be labeled or not in the plot. You can just add more microRNAs, add more features to the plot or not. It will cause the plot to draw again, and this microRNA should be marked on this plot now. We can also select whether those are log adjusted or crude values, and whether we should use adjusted or not adjusted p-value in the plot. The next tool is the imputation of missing data. In this tool, we can select the data with some holes in it. Those should be an empty cells, and as we will load it, we can see the input preview of the data and the missing variables. It will take some time to generate those plots. We can see the input data preview, the missing values in the data set, showing us that 2.9% of the data is missing in this file, which variables are missing, and if there are interactions. So this and this microRNA is missing appeared in 6 times. We also do a PCA for complete cases before imputation. This is also an interactive plot. And then the data set is being imputed. We can download this imputed data set without any missing values for further analysis. We can also compare the principal component analysis for all cases after imputation here with this interactive plot. There are 2 options for the data imputation. One is predictive mean matching. The second one is replacement with a mean. The next tool is correcting batch effect using Combat. In this module, we have to load the file with some kind of batch effect. And let's wait for plots to show. So here we have 2 batches, the samples from Łódź and from Boston, and 2 classes. We can see the initial analysis, the PCA for cancer versus controls and for batches. If we consider it to be a significant batch effect, here we have the corrected data set, and we can download batch corrected data and see the PCA after batch correction. This correction can be done using only batch variable or also batch and class variables in the join tool. And the last tool is the heat map generator. In this tool, you can generate a nice heat map for your data. So here we see the heat map produced by the software. We can change the expression metrics. We can change the legend position. We can change whether we want to include just a class or class and batch or just batch. It will add to the legend. We can change the legend size. We can change the plot height so it can be more readable, and the plot margin if we think we need it. One more thing is that we can center and trim the values shown here. So for example, if we want this scale to be centered on 0, we can just leave it on 0. If we want to trim higher expression values, we can set to trim the maximum to 2, and it will make it look a little bit different. Let's say it corrected to 1, so we can see some differences or not. 1.5. Sorry. Yeah. And we can z-score it before plotting, and we can, for example, trim a very low expression values, so we will have a better scale here. Well, so this is it. I hope you enjoyed this tutorial. If you have any questions, feel free to contact us at any second, and I hope you will find our tool useful. Thank you.